Our brain's response to the word radioactivity usually takes us into the realm of superheroes, or into some dark, reimagined, post-apocalyptic world after a nuclear fallout. There is rarely a middle ground. However, 120 years ago, the world had a completely different perception of radioactivity. In fact, it was considered to be a miraculous reservoir of health and vitality. From toothpaste and watch dials to water and butter, radioactivity was everywhere. So, what happened? How has this marvelous discovery, which was considered one of humankind's greatest achievements, turned into something that scares countless people across the globe? Well, let's start with the basics. Everything we see around us is composed of elements with stable atoms. The subatomic component responsible for maintaining the stability of an atom is called the nucleus. Now, imagine that you're about to sneeze, but it hasn't quite come out yet. How does that feel? It might be strange to describe, but that's exactly what certain atoms experience all the time: the urge to expel the excess and regain stability. Inside an atom's nucleus, there are positively charged protons and neutral neutrons. These nucleons are held together by a glue called the strong nuclear force. This strong force cancels out the repulsive electrostatic force of like-charged protons and keeps the nucleus stable. The nuclear force has a short range of action and is dependent on the ratio of neutrons and protons present in a nucleus. However, we see that the balance between the forces starts to waver in a nucleus where the number of neutrons exceeds the number of protons. A nucleus that exceeds the threshold number of neutrons and protons that the strong nuclear force can hold together comfortably will become more unstable. More specifically, these scenarios give rise to unstable isotopes of elements. Just as your body, through a series of expansions and contractions, expels a substance with a sneeze, similarly, the unstable isotopes of elements fling out different particles or forms of energy to restore balance between the forces in their nucleus. During this process of attaining stability, they change into a new nucleus. It is exactly this property, namely turning into something new to attain stability, that we call radioactivity. The process by which it transforms is called radioactive decay. A nucleus can undergo nuclear or radioactive decay through the emission of alpha, beta, or gamma radiation, and sometimes a combination of all three. The alpha particles are relatively heavy. They can travel only a few centimeters in the air and can be easily stopped by a sheet of paper or plastic. Beta particles have higher energy and more penetrating power than alpha particles, but are less ionizing in nature. They can travel through the air, but can be stopped by a thin sheet of metal or even protective clothing. Finally, the most energetic and fatal form of radioactive decay is gamma rays. Yes, these are the type that supposedly turned Bruce Banner into the Hulk. This is a form of high-energy light emitted by a nucleus that is left at a higher energy state after an alpha and beta decay process, but must still return to a more stable, lower energy state. A nucleus can undergo all of these decays spontaneously and transform into a stable form within seconds, years, or even centuries. This rate of decay is decided by what we refer to as the half-life of the radioactive substance, which measures the time it takes for a given amount of the substance to become reduced by half as a consequence of decay. One cannot have a discussion regarding radioactivity without a mention of the famous scientist Marie Curie. Her lead-sealed radioactive laboratory, notebooks, cookbooks, and furniture contaminated by radium are a testimony to her contributions in the field. She is also the only person to win the Nobel Prize in both physics and chemistry. The discovery of radioactivity and radioactive elements came through Marie and Pierre Curie, along with Henri Becquerel in the early 1900s, opening up the gates to a completely new field of atomic physics. That eventually led to the discovery of different components of atoms and nuclear energy. For example, radioactive elements like uranium-235 and plutonium-239, when bombarded with neutrons, release an enormous amount of energy. Believe it or not, just 1 kilogram of uranium-235 can produce almost 24 million kilowatt-hours of power through nuclear fission. In comparison, 1 kilogram of coal can only produce 8 kilowatt-hours of energy. This is why it has been said that nuclear energy can power entire cities for decades. Needless to say, the sheer power and potential of carefully handled radioactivity and nuclear energy is immense. But, as is true with all great things, radioactivity also comes with some risks. Radiation as a whole isn't dangerous. Light bouncing off a reflective surface, the microwaves heating our food, or the signals received by our mobile phones are all different forms of radiation. However, there is one kind of radiation that is particularly harmful to all biological forms: ionizing or nuclear radiation. A radioactive material during its decay process emits ionizing radiation, and when a living being is exposed to such high-energy radiation, it doesn't make someone radioactive, but rather a likely victim of radiation poisoning. Radiation poisoning from nuclear radiation can easily damage the molecular structure of DNA and harm living cells. A heavy or prolonged dose can prove lethal, as these rays are carcinogenic. What happened at the Chernobyl reactor decades ago has left mankind shaken to this day. One incident of a reactor meltdown, and 4 square miles of land are rendered uninhabitable for generations. Not to mention the thousands of lives exposed to the indelible effects of radiation poisoning. The remains of the reactor sit inside a containment structure made of thick steel walls. Cleanup protocols will be continued until 2065. The Fukushima Daiichi reactor that was hit by a tsunami in 2011 forced the evacuation of thousands in a 20-kilometer radius of the incident. The authorities are still cleaning up its surroundings, including removing and disposing of the topsoil in the affected region. Although it may seem that the word radioactive has a negative connotation, surprisingly, radioactivity is not always harmful. There is a saying in toxicology that the dose makes the poison. It's true that when a person is exposed to unregulated amounts of radioactive material, it can cause severe genetic mutations and cancer. However, when regulated, it can also cure cancer. Radioactive iodine is used in radiation therapy to treat cancer and for imaging in the thyroid gland. Radioactive technetium is used for the detection of heart, bone, and other organ defects. Radioactive C14 carbon is used in carbon dating, which helps us determine the age of things. In some countries, fresh produce is lightly irradiated before packaging to kill off the germs on the surface of fruits and vegetables. A tiny amount of americium-241 is used in smoke alarms that help save thousands of lives every year. Quite simply, radioactivity is everywhere. But hypothetically, if you end up backpacking to an unknown land and the Geiger counter in your bag starts crackling, the best thing you can do is run.